Okay, so let me just now share my screen. Okay. So anyway, we just had those simple things we needed to work on. I know as I read your personal mathematics history, I'm glad that you are there. So we can, yeah, I'll try to be on pace. If I see you, you know all those that I am already discussing, then we can just move on so we can proceed to the real topics of college algebra, especially functions, okay, because that's what we will really be looking at. So now, just to remind us of scientific notation, because this is one of the areas in math that's had really been very useful, particularly in the sciences, when we have very big and very small numbers. Then we just use scientific notation to present those numbers. So just a little history of scientific notation. So it was as early as the 3rd century BC when Archimedes, right, was able to attempt to use the scientific notation numbers. And it's so interesting that, he thought of this because he tried to estimate the necessary number of sand grains to fill the universe. Isn't that interesting? All right, mathematicians would just, try to go beyond their own world and think of something bigger than them. And he is estimated that you add 63 zeros to 1. Oh, 63. So for 1, then add 63 more zeros. And he's saying that that's the total number of the grains of sand that would fill the universe. I just remember what God told Abraham, yeah? You
Mhm.
look at the stars, okay, and the grains of sand, and that's how much your was that your the generations that would follow you, your children, kind of thing. Yeah, but anyway, it's that a big number, 1 2 times 10 to the 63rd power. So that's the beginning of scientific notation. And so just to remind us, definitely when we talk about scientific notation, our a number, okay, before the times 10 to a certain power is supposed to be between 1 and 10. In other words, you don't, even if you find 24 times 10 to the 15, you just have to transform it so that that main base of the main value would just be less than 10. Great. So that's what it is. We now have 8 times 10 to the 10th power. Okay. So just a little, yeah. So some examples, definitely. Yeah, the distance from Earth to the Sun is 1,000,000,000,000,000,000, 150 billion meters. So I think you know what to do. That just, put a decimal point such that you get a number between 1 to 10, 1.5, and then count the number from that decimal point. So that we're saying, let me change this to high laser pointer. Okay. So we're saying we count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so there's 11 from the decimal point to the right. Okay, though we'll have 1.5 times 10 to the 11. When we now have a very small number, and that is the mass of average human cell. This time we move the decimal, we move the decimal point to to the right in that kind of thing. In other words, so for number that is too big, you have to move, you count, all right, from 0, 0, 0, 0, 0, and move to the left until you get to a point where you just get a number less than 10. But for a negative, which is a decimal point, you move your decimal point to the right. And so we count 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 until 1. So 1 times 10 to the negative 12. Of course, the diameter of the moon, well, you know what it is. So it will become 3.474, and there will be 6 numbers to the right. So that's times 10 to the 6. The temperature at the core of the sun, from 1.56, count the number, the 5, 6, 0, 0, 0, 0, 0, and that would be to the 7th. Okay. And of course, the estimated number of cells in the human body. Right. And so there are 14 zeros after the 1. 3, 6,
Can
12.
I
3, 6, 9, 12, 14.
can I please ask
Yeah?
on the one diameter of the moon,
Mm-hmm.
3 or 7, 4
0.474. And then there are 6
times 10 to
numbers. Yeah, if you put the point here, all right, 3.474, and you count the numbers 1, 2, 3, 4, 5, 6. You see that? 1, the 0, 2, another 0, 3, 4, 5, 6. So that's 10 to the 6. So you move and put the point or the decimal between 3.474 because you only need a value. This number should be less than 10.
yeah.
Are you okay? Yeah. So
Which
count.
number should be greater?
Huh?
The first. Which number should be greater than 0?
This first number, greater than 1 but less than 10. So it is 1.5. That is between 1 to 10. 1 is between 1 to 10. 3.474 is between 1 to 10. 1.56 is between 1 to 10. And then 1. So always, like you count the numbers 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't stop at the 15. Move on to 1.5 because you need a number less than 10. So that's why this is 11. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Don't stop there. You move up to the 1 because you need a number greater than 1, between 1 to 10. All right, and so 1 times 10 to the negative 12 because this is a decimal number. Let's count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 until you get to a 1 point something. So 1 times 10 to the negative 12. Is that okay? Now, in this case, you move to the left, all right? 1, 2, 3, 4, 5, 6, 7 before you get the 1.56. So that's 10 to the 7. In this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. You end there because you need a 1. So it will now be 1 times 10 to the 14. All right. So I hope. Okay, let's have right. Okay, so that's scientific. I just thought, well, the scientific notation. There will be some exercises maybe in the book that I will be asking you to do. Now there are times when you need to change the scientific notation to a standard form. Yeah, so you just have to reverse the process. If I have 1.496 times 10 to the 8, what will you do is, yeah, you move the decimal point. All right. Yes. So the decimal point, and like this is 1, 2, 3. So how many zeros will you add?
5.
5.
All right, 5 zeros because you are moving. So say 1, 1, 2, 3. That's 10 to the 8. So you need 5 more to have a 10 to the 8. So it will now be 1, 4, 9, 6. Add 5 zeros so that you'll have 8. 1, 2, 3, 4, 5, 6, 7, 8 numbers after the 1.49. All right. If you are changing the 149,600,000 to do scientific notation, you move 1, 2, 3, 4, 5, 6, 7, 8. You end with 1.496, and there are 8 decimal places. We call this the places, and there are 8 of them, so that's why you say times 10 to the 8. Right. Now, is one thing with our book is the odd numbered exercises have answers. So you can go to the appendix so that if you try to do the odd numbered exercises, then you work on it first and then check whether you get the answer correctly. Okay.
Did you?
Yeah, so let's just proceed in here. Okay, so let's try doing this. Let's try to do the scientific notation and see, so that I can explain some more if something is not okay. Look at these numbers here and then work on the scientific notation. Yeah, just try and then see whether what the explanation had been clear. So this one was still 2014. Maybe this time the debt per taxpayer will already be that, much bigger because this was some like 10 years ago. Okay, let's see. Yeah. There are 5 of you, so each one will give your answer per there are A, B, C, D, E. Okay, who wants to give an answer for letter A? Yes.
1.
Yeah.
1.5 times 10 exponent 5.
All right. So that's now 1.52 times 10. So we're counting. Oh, sorry for my I don't know what happened to my writing. 1, 2, 3, 4, 5. Okay, 10 to the 5th. Right. Okay. Let me erase that. I don't know. I made black. All right. Letter B.
Manish.
Uh, mm,
Yes, Manish, yes.
7.158 times 10 to the 9.
Okay. Everyone has that? It's good. 7.158 times 10 to the 9. Yeah. Letter C.
8.55 times 10 to the 13th power.
All right. 3, 6, 9, 12, 13. Very good. So 8.55 times 10 to the 13. Letter D. Yeah, this one is a very small number, decimal, so you know that the power will be negative, right? Okay. So just count to the right until you get to 3.34. And how many places would you have counted? Oh. Sneh, you want to give an answer?
I can't even see. -9.
Yeah?
3.34 times 10 to the -9th power.
All right.
Yeah.
So you're counting one. There are how many zeros? 2, 4, 6, 8.
Choose
6, 7, 8, 9. You move to 3.34. Yeah. Okay. So there are 2, 4, 6, 8. Move to 3 point. And there will be 9 places there. So that will now be 3.34 times 10 to the negative 9. Is that okay? Yeah. So for letter E, you count the number of zeros until you move to 7.15. So what will that be? How many places? Yes. Okay.
7.15 times 10 to the -8.
Oh, all right. So, count. 1, there are 2, 4, 6, 7 zeros, but you just have to move to 7.15. So then you'll have one more. So 7.15 times 10 to the -8. All right. 7.15 times 10 to the -8. Oh, I hope, yes. So that's how it is with our scientific notation. Yeah, you will have more things in the book that you can practice on. Okay, so let's now proceed. Converting now to standard notation. So it's the other way around. And you now have 7.03 times 10 to the 5th, and then change it to standard. We call it standard when you'll just add zeros as needed. Okay. All right, so for letter A, how many zeros will we add?
3.
All right, so you now, okay, so you will now change it will become 703, but then that's 10 to the 5th. So you're moving your decimal place to the right and add 3 more zeros. So 70,000, 703,000, I should say. 703, so that will now be 703,000. Now, okay, letter B. We add how many zeros?
10.
9.
Yeah, I think you'll have to add 9 zeros, right? Because you already have
Yeah.
16, then that's two decimal points moving. And then you have 10 to the 11, so you have 2 for the 16. You just need to add 9 more zeros. Okay. So you now have minus 8, 1, 6. So that's 1, 2. You need 11. 3, 4, 5, 6, 7, 8, 9, 10, 11. So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, sorry for that. Okay, that will now be 816,000 million billion. So we just have to 16 and there are 11. So there are 2 decimal places from the 8.16 to 16. And so you need 11. So you will have to add 9 more zeros. How about letter C?
Add 10.
You move to the left now because you need a decimal, right? So it will now be negative 13. So it will be how many zeros that you will be adding?
12.
12.
Yeah.
You take the exponent and you minus one number.
All right. So about 12, right? Because it will now be 0.00. So this is 3.9. Yeah, you will be moving it to the left. So 1, 2. So it will now be point. Yes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 39. Okay, 2, 4, 6, 8, 10, 12, 39. Yeah, so you have to just 1 because there's a 3.9 there minus 1 for the number of zeros. All right, and so for your letter D, that's 8.0, 0.00000. So how many?
Has a negative 13.
Yeah.
5. 5 zeros.
So if this has a negative in front of the exponent, then you go to the left.
I know, I just messed up when writing it on my paper.
5 zeros before 8.
All right. So you'll put 5 zeros before 8.
5 zeros before 8?
Yes.
After the decimal.
But you move to the right. So from after the decimal, as you move on, because you're moving your decimal to the left. So after that decimal, if of course there's a 1 number after the decimal, that will be the 3. So you always subtract one number on the 13, right? That's why we're adding 12 zeros. So for the 8 times 10 to the negative 6, all right, the decimal in that 8 is here. That's where the decimal is. So you're now moving to the left. So the decimal is at 8. You move to the left. There's already 1 decimal there. So you have to just add 5 zeros. So it will now be 0.1, 2, 3, 4, 5, 8.
Oh.
Now, if you change it to the scientific notation, then what you do is, you now 1, 2, 3, 4, 5, 6. That's why that's 10 to the negative 6. But if you are changing it to the other side, then you will have to add the number of zeros that you will be adding would be one less that number that you have as a power after the decimal. So for the 3.9, you're adding 12. Yeah, zeros to the left so that it will become a decimal. All right, so I think some of those shortcuts things that you need to remember. Okay. All right, now let's have one problem here. An average human body contains around 30 and 12 zeros, 16 for 12, okay, 13, 12 zeros, red blood cells. And it says each cell measures approximately 0.00008 meter long. So first, write its number in scientific notation. And then we'll be using some rules of exponents in order for us to find the total length if the cells were laid end to end, and would like to write the answer in both scientific and standard notations. If you use your calculator there, then that calculator will also just give you scientific notation. So let us first change. Let us first change the number of red blood cells in scientific notation, and then the length of each cell also in scientific notation. And then we use our understanding of exponents. I mean, our rules, product rules, I mean, the rules of exponents, and apply in multiplication. Yes, I think you are. Okay, so we'll see. All right. So our the number of red blood cells in an average human body is, how is that in scientific notation? 3 times
10 exponent 30.
All right. So please just count. Okay. After the 3, there are 13 zeros. So this will be 10 to the 13. Okay. For the length of each cell, that will be 8 times 10 to what power?
-6.
Yes.
Negative
You move
5.
now. So 1, 2, 3, 4, 5, 6, right? Until, so you get to 8 point something. There are 6 of them. There are 5 zeros plus the 8. So that's 10 to the negative 6. Correct? Okay. Now, to get the length, all right, the total length of the red blood cells when they are laid end to end, what do? We multiply, right? So because per cell has a length of 8 times 10 to the negative 6. Right. So we have to multiply. So for every cell, the length is 0.000008 meter long. So that's for per cell. And there are 3 times 10 to the 13 cells. So we'll have to multiply. And according to the rules, the product rules, let's first multiply the numbers. 3 times 8 is 24, okay? And then what do we do with the exponent? We'll have to add. So 13 minus 6 is
7.
7. But that is not yet the scientific notation, because the scientific notation is your number should be less than 10.
Mhm.
So this will now be 2.4 times 10 to what power? I
The
just
8th power.
to the 8th power. Yes. And if we change this to standard notation, then after the 4, we'll add 7 zeros, right?
0.
So you now have 2, 4, 1, 2, 3, 4, 5, 6, 7. So this is now 240,000 meters. So that will be the length of your red blood cells. If they are laid end to end, it will be 240 million, I should say. 240 million meters. So I hope you got it. Any question on that? Okay, so I'll just move on to the next slide. So that's scientific notation. Yeah, just some understanding on root, square root. You know that many of the formulas in math would involve square root. You remember I have shown some formulas previously, your quadratic formula has a square root. If you're familiar with Pythagorean theorem, which says the sum of the squares of the two sides of the right triangle is equal to the square of the hypotenuse. All right, so I hope you remember that. And because there are squares, then to get the length of one side or the length of the hypotenuse, we will be making use of square root. So this one is just reminding us of how square root is being evaluated. So in math, when we talk of there's a thing called principal square root. Okay, let me just explain. If I say the number 4, what numbers will I multiply by itself to get a 4? So you know that 2 squared is also 2 squared is 4, but at the same time, negative 2 squared is also 4. But we are more interested in the principal square root, which is the non-negative number. So that if I say, what's the principal square root of 4? Their answer is 2. Although negative 2, if you square, it will also be equal to 4. So we talk about radical expression, the symbol radical, yes, this one, okay, is a radical symbol. And of course, the radicand is the one under the radical symbol. So just terminologies, radical is the symbol, radicand is the number, and under that symbol, and the whole thing is called radical expression. So that I will be using these terminologies, and so it's important that we understand these terms: radical, radicand, and radical expression. So just a little history of the radical sign. It's good to know where it came from. Yeah. You know, it was first used in print by Cos that was long time ago, 1525. And it says it is the manuscript form for the letter R. And that letter R, the Latin word is the R is the Latin word for radix or root. So that's the idea. So they have this kind of thing of like in the beginning it was just All right. In the beginning, it was just like this. There's no roof on top. It's just like a check mark, which is associated with the letter R. So then it appears like a musical note. And then whenever they have a long expression under that is associated with that radical sign, the radicand, they just use the parenthesis. So it will now be this symbol and put parenthesis. There was no roof, but it was Descartes in 1637 who thought that perhaps it is better to use what we call vinculum. When you put something on top, we call it vinculum. I mentioned this in the repeating decimal. And so now this symbol was used. So instead of just putting parentheses to group the radicand, then they used the roof. And so this one was introduced by Descartes, and this is now what we are using nowadays. Okay. So that's just a little right. So let's proceed. Okay. So now just because we are dealing with square roots, we need to understand the different perfect squares, because in our evaluation of square root, we always would have to consider what are the perfect squares that would be a multiple of a certain number. Okay, so you have now the perfect squares when you multiply the number by itself. And so if you can remember all those numbers that are perfect squares, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, and you can move on and on. I have presented there the chart of perfect squares until 30. So that when you see 529, you should know that that is a perfect square, because that is obtained by squaring 23. 23 times 23 is 529. If you have 361, that one is a perfect square, because that is the product of 19 times 19, or 841. But anyway, I don't think we'll get to those very, very big numbers, but maybe up to 12 or 15, yeah, or 20. When you now have 169, then you know that one is 13 squared. So these are some of the perfect squares. And so a variable is a perfect square if we're now talking of variable that are perfect squares. Once you see a variable that has an exponent that is even, then we know it is a perfect square. X to the 4th, x to the 16th, x to the 100, x to the 26, and so on. So anytime your exponent is an even number, then that is a perfect square. And therefore, if we say x to the 4th is a perfect square, the root of that will be x squared, because x squared times x squared is x to the 4th. So it's easy to get the square root of a variable. All right, the square root of a variable is just whatever is the exponent, we just divide by 2. So that if you now have the square root of x to the 16, then it must be x to the 8, because you divide 16 by 2. So we need to understand the root of the numbers and also the root of the variables based on the exponent. So the exponent of a variable that is even, you get the root, you divide the exponent by 2. All right. So just evaluating square roots of our numbers. That one, just say it out loud. What's the square root of 225?
15.
Okay. So that one, I hope that one should be remembered. Yeah. It's 15 because 15 times 15 is 225.
300.
All right. Now let's have this. The square root of 81.
3.
3.
Yes.
3.
First begin at the inner one. Okay? So it will now be square root of 81 is 9. And then, yeah. So the square root of 81 is 9. And the square root of 9 is equal to
3.
the square root of 25 minus 9.
25 minus 9 is 64.
All right. So please do first whatever is the radicand. All right, the square root of 25 minus 9, subtract 25 minus 9 first, and then get the square root. So please take note that that is not the same as the square root of 25 minus the square root of 9. All right, they are not equal. Do not, some people will say square root of 25 is 5, the square root of 9 is 3. You don't do that. All right, you do first the operation inside. So 25 minus 9 is 16, and the square root of 16 is 4. Good.
4.
All right, and for letter D, you just have to do the evaluation. So, say square root of 36
Wow.
is
That's good.
6, and the square root of 11 is? Oh, 11. I already gave the answer. The square root of 121 is 11. So, 6 plus 11 is equal to 17. So, this one is 6 plus 11 is 17. That's why I'm saying it's good to put in memory a few of these squares so that it's easy for you to get the square root, maybe up to 20. That won't be very difficult to remember. All right. So that's our square roots. Okay, let's move on. Okay, now, so to simplify square roots, especially if you're dealing with variables, we usually use, okay, the same as the product rule. All right, you remember our product rule. So that when you have now the square root of AB, it's just the same as square root of A times square root of B. Okay. And therefore, if you have a square root radical expressions that would have letters and numbers, and there are radicands, that's not really a perfect square, but you can find perfect squares from the radicand. So what we will do is take out the perfect squares and then move on with the evaluation of the radical expression and do simplification. So let's try to use the product rule and the thinking of the different perfect squares. So like if I have the square root of 300, 300 is not a perfect square. But 300 would be would be the product of two multiples such that one of them is a perfect square. Right? And that would be 300 is the same as 3 times 100, correct? Yeah. I used 100 because 100 is a perfect square. So we now say that the square root of 300 is equal to the square root of 3 times 100. And according to the product rule, that is just the same as the square root of 3 times the square root of 100, right? Now, the square root of 100, you are able to get. The square root of 100 is 10, so that you'll just have 10. It's good to put the whole number before the radicand. So you'll now have 10, the square root of 3. So that's how to simplify square roots. Take out a multiple that is perfect square and then simplify. The one that is not a perfect square will remain to be under the radical, and it will be the radical. Now, let's see. Will you please try letter B? All right. This time, this has already letters.
What?
So letter B. So first think of what number is factor of 162 that is a perfect square. Right. So let me first just erase that so we can write the. So with 162, 162 is a product of which two numbers, such that one of them is a perfect square?
81.
81.
Yeah, 81 times 2, right? Okay, so we now have, okay, so we can write 162 a to the 5th, b to the 4th. Why is my writing like that? Okay, can be written as 162 is 81 times 2.
2.
Okay? Now, we have now the a to the 5th. Separate that as one having a power that is even. So that will now be a times a to the 4th, right? Reason for that is because anything with an even power is a perfect square. And therefore, you will remain with b to the 4th. So we can now write it as put together all the perfect squares. So 162 a to the 5th, b to the 4th will be 81 a to the 4th, b to the 4th times 2a.
I didn't
You
get
have to
A
check.
to the fourth.
Yeah, a to the 4th, b to the 4th times 2a. So you will have
Mhm.
A exponent 1
mm.
times A exponent 4.
So if you want to check whether that's correct, 81 times 2 is 162. A to the 4th times a is a to the 5th, then you have b to the 4th. Now, 81 a to the 4th, b to the 4th is a perfect square. Extract the root. And that will now be square root of 8 to 1 is 9. Square root of a to the 4th is a squared, right? Because we're just dividing the exponent by 2. Then, square root of b to the 4th is b squared. What remains as a radicand will be 2a. So you now have 9a squared, b squared times the square root of 2a. Okay, that's fine. So I think letter C, you're able to do. Square root of 50x squared y cubed z. Okay, what's your answer?
5x.
Who wants to share the answer that you got? 5. Yes, go ahead.
Okay, A is square root of 3 times the square root of 100.
Yes, he's asking for C.
See.
Oh, wait, we now have 50x squared y cubed z, right? For letter C. So your number is 50. Okay, who wants to just share the answer that you got?
Well, I
Anesh,
got
yes?
5,
5.
then square root 2x squared y cubed z.
All right, but you still need to get the square root of those variables.
Yeah.
Oh,
Yes.
I
Yes, Abigail,
in order
yes?
to, in order to
5.
get 50, you need times
Mhm.
10. 2 times 25.
Yeah.
So it'd be
You think
X.
of two numbers that when you multiply those two numbers will give you 50, but one of those should be a perfect square. So you
10.
don't want to use the 10 times 5 because 10 is not a perfect square, 5 is not a perfect square. So what would be those two numbers that one of them is a perfect square?
25 times 2.
Yes, that's 25 times 2. And then your x squared is already a perfect square. But your y cube,
Yes.
you'll have to factor it as y squared and y. And then the z
Yes.
remains as it is.
Yeah.
Okay.
oh,
Yeah. So you now have your 50 x
Y
squared
squared.
y cube z can be factored as 25 x squared y squared times 2yz, right?
oh,
So your 50 is 25 times 2. Your x squared, your x cube is x squared times y. You want to isolate one letter with a power that is even. And then your y squared is there. Okay, I mean x squared, y squared, y cube is y squared times y. And then a z. So I think the x squared is already a square, perfect square. So your
It
50x squared y cubed z will be written as 25x squared y squared times 2yz. Is that okay? What's your final
yes.
answer now? Then we extract the root. And according to the rule of the product, you extract now the root of 25x squared y squared gives you 5xy. Then retain as radicand your 2yz. Is that okay?
Yes,
Yes.
now I get it.
Yes. All right. Yeah. So you will have to consider also the variables. The variables.
One sec.
Is that okay?
Yeah.
Yeah.
It
All right.
didn't include the x and y. I put the square because
Yeah.
the roots.
Yes. So you get all the square roots of all the ones there as long as they are perfect squares. All right. And whichever is not a perfect square, it should remain as radicand. Now, okay. This time, that's supposed to have multiple square roots. That's right, doing that. Okay. So what happens there is you first express the product as a single square root. Now, following again your rules of exponents, all right? They have the same they have the same under the radical. So that for letter A, if I say the square root of 12 times square root of 3, right? So the square root of 12 times square root of 3, put that under single square root, that will now be 12 times 3. And 12 times 3 is 36.
36.
And the square root of 36 is 6. Yes.
Oh,
Yeah. So combine them first, do the multiplication before you extract the root. Okay, do letter B and C and D.
the 110.
Okay, you can do mental math if you will, no problem, if you want to do so.
Mental math.
Mental, yeah. Without computing, without using your pen.
You need 10%. CND.
So do you agree that letter B is 10?
Yes.
Yes, good. 2 times 5 is 10 times 10, okay? And so the square root of 10 times 10 is 10. Good.
Okay, now
Now, letter C. Now, I am putting there, assuming that x is greater than 0 because you cannot extract the root of a negative number. So, it's always, whenever we use x, we would want that x to be greater than 0. Answer for letter C. Can you do mental math?
10x.
Okay.
10x.
Yes, 10x. Everyone agrees?
Yeah.
Okay. Yeah, because that's the same as 100x squared. 50 times 2 is 100. X times x is x squared. And so the square root of 100 is 10. The square root of x squared is x. Okay, good. Letter D. You done? Okay, so putting that as a single square root. 8 times 12 is 96, right? Then x
Yes.
to the 5th, then y to the 5th.
Mm-hmm.
Now, but 96 is a multiple of what two numbers? One of them should be a perfect square.
16 times 6.
16. All right, that's great. Okay. So this is now the same as the square root of 16 x to the 4th, y to the 4th times
6.
6. Yes.
6.
X, y, correct?
Yeah.
So we're taking out the fourth, remaining is xy. Therefore, final answer
Four.
is square root of 16
4x
is
to
4. Square root of x to the 4th is x squared. Square root of y to the 4th is x squared. What remains as a radicand would be 6xy.
Yeah.
Yes. Good. Right. This time quotient. It's just behaving a fraction, but it's the same style as our okay. So just the quotient rule. You also get the square root of the one on top, the square root of the one at the bottom. Okay. Square root of 5 over 36. Answer?
Square root of 5 over 6.
All right. So because that can be written as the square root of 5 divided by the square root of 36. So it will now be 36 equals square root of 5 divided by 6. Letter B.
X over 3 y squared.
Times what remains in the or under the radical, and then the radical, or remains to be the radical.
Is it not going to be 2x? Oh, no. Yeah.
2.
Square root.
2 will be under the radical.
All right. So you
Yeah,
separate. You now have 2x squared over square root of 9y to the 4th. May just for a while. Let me erase. I am writing like.
use the square root.
Let me erase that part.
To the square root 2x over 3y.
Okay. Over the square root of 9 y to the 4th. All right. For the square root of 2x squared is only x squared that is a perfect square. So take that out, right? X. What remains is square root of 2 over 9y to the 4th is a perfect square. And that will be 3y squared.
It isn't y squared above.
You can write it as some people would want it as the square root of 2 times x over 3y squared, but that's not necessary. I would rather have, I would rather have that as just x, the square root of 2 over 3y squared. So the idea only is that you get the square root of the numerator and you also get the square root of the denominator.
We don't want a square root in the denominator.
Right. So x, the square root of 2 over 3y squared. Now, all right. So it's the same. This time you combine numerator and denominator into one square root. Simplify the fraction, then simplify the square root. Or I'd rather have you like letter A. You first divide 12 by 3 because that's not under the square root anyway. So 12 divided by 3 is, okay, let's do that together, is 4. And then it's times the square root of 6 over 2. Put that under one root.
Yeah.
Yes. And therefore, 6 divided by 2 is 3. Your final answer is 4, the square root of 3. Okay. This time, try the ones with the letters, with the variables. They are both now under the square root sign. So put them together and then simplify.
That's the easy one. You should give us four.
Naturally.
Is that 11?
Looks like it.
Like, it's 1 and 11?
Yeah, 2, 3,
so.
4, x to the 11th, y over 26, x to the 7, y.
Yes, that's right. And then you divide to 34 by 26. And then do the division, x to the 11, x to the 7, and y.
How do you divide sorry. Minus.
Yeah,
It's
subtract the exponents. So what's 234 divided by 26?
9.
Good.
I use that.
X to the 11 divided by x to the 7.
X to the 4.
Good. Y and y, that will just be equal to 1, right? So we can just cancel
Yes.
it out. All right, good. Final answer?
9x4.
3x squared. Correct?
Yeah, I do.
The square root of 9 is 3. The square root of x to the 4th is x squared. You just be careful. Divide the exponent by 2. Okay.
That looks simpler. Oh, there's more.
The last one, letter C, for this exercise.
What is that, 9A?
9a 5b
e to
14.
the 14 over square root of 3a to the 4th, b to the 5th.
There's a square. That is just 3. And then, a, b, 9.
Three AB. Wait, that's AB.
Yeah, okay. So 3ab is the one that will be in the radicand. As the radicand, what will be the one with a A being a perfect square that you'll extract the root.
B4.
You flip it. Oh. Yeah, with your printer.
She, I got B4 and 3AB.
All right. B to the fourth square root of 3AB.
I'm the one who's wrong.
B to the fourth
No.
square root of 3AB. Is that okay?
Yeah.
Yeah, let me just erase. Yeah, it looks like. Yeah, because you got this one is 9 divided by 3 is 3. A to the fifth, oops, divided by A to the fourth is A. B to the 14th divided by B to the fifth is B to the 9th, right? And so you now have the square root of, it's only the B to the 9 that you can get perfect square. That's B to the 8. 3AB equals B to the fourth square root of 3AB. My writing is not. I think I need my iPad to be at a certain position that I can write well. All right, B to the fourth square root of 3AB. Great.
How did you simplify the B to the 9?
Oh no,
B to the 14th divided by B to the 5th is B to the 14 minus 5. You subtract, yeah? Okay. A to the 5th divided by A to the 4th is A to the 5 minus 4. So that's why it's just A. So 9 divided
No,
by
I mean,
3. Yeah? Where did we get the B to the 9?
no, I know where you get the 9. I mean,
Uh-huh. Then
the
we
4.
split B to the 9 to B to the 8 times B. Because we want one of the exponents to be even. Okay?
Yeah.
Yes. All right. So we're just playing with numbers, letters, and this kind of thing. So think of it as a game. Adding, subtracting, depending on. All right. So this time, just suppose we have square roots that are being added or subtracted. Okay, so it says when we have addition or subtraction of square roots, the first thing we'll have to do is simplify the radical expression. And then see whether we have terms that have the same radicand. When I say same radicand, having the same number under the square root sign. So an example here is if I add 5 the square root of 12 plus 2 the square root of 3. So we can write this as 5. This 5 the square root of 12, as we have discussed a while ago, can be written as 5 times the square root of 4 times 3, because we want our 12 to be factored such that one of them is a perfect square. Right. So we now have the 5 square root of 12 can be written as according to the product rule, although you really don't need to do this step by step. If you already can have the mental math, that's fine with me. But that's how it is. 5 the square root of 12 is the same as 5 times the square root of 4 times the square root of 3. But the square root of 4 is 2. So that will now be 5 times 2 is 10 square root of 3. So 5 the square root of 12 is the same as 10 the square root of 3, as you know what we have learned a while ago. And so the final expression becomes, instead of 5 square root of 12, it will be 10 square root of 3. And we now have the 2 the square root of 3, which you cannot anymore simplify. That's already the simplest form. And because this is square root of 3 and square root of 3, they are the same, having the same radicand. What you just do is add only the numbers associated with it. So that will now become 10 plus 2 is 12, the square root of 3. Right. So what we do is try to simplify the radicals such that you'll get the same radicand. And when you already have the same radicand, you can do the process of adding or subtracting. Okay. So like letter A, or immediately you can tell me the answer. Answer for letter A?
7. 6, the square root of 7.
6 to
Yes, 6, the square root of 7. Very good. Yeah. So once they are they are the same, having the same radicand, just add the numbers or subtract the numbers. Okay. So let's try. Okay, maybe you can do letter B, then we'll work letter C together. Letter B. You will have to
12.
simplify the square root of
5.
20. Can you do mental math there?
Yeah.
Yes.
yeah,
Good.
9, 9 to 5, right?
yeah.
Yeah.
It's
Square root 20 is a product of 4
4
times
times
5.
5.
Oh, yes, 4 times 5. But the square root of 4 is
2.
2. Multiply that by 6.
6.
Yes.
Yes, sir.
So that's 12. Final answer.
Is it 13?
Okay. Yeah. Yeah. If you can do mental math, I'm very open to that. All right. So is the answer 13? The square root of 5? Okay. So just for illustrate, for, yeah, square root of 5. This is the same plus 6 times the square root of 4 times 5. So it will now be the square root of 5 plus, but square root of 4 is 2. So that's 6 times 2, the square root of 5. So you get square root of 5 plus 12 square root of 5. Of course, you know that when you just have square root of 5, that is the number associated with it is a 1. So 12 plus 1 is 13. So you'll now have 13, the square root of 5. Great.
So we have to do a C.
Is that okay? Oh, we'll see. Can you do mental math for letter C?
Oh, man.
Okay, then use your pen.
3.4.
Who has an answer? Yeah, answer.
Not sure. So,
Can you put them together or yeah. For mental math, what will be the first expression there? 3 square root of 24x square, x cubed. So 24 is a product of 6 times 4, right?
Yes.
Yes,
Mhm.
so the square root of 4 is 2. So that will now become 6. Then the x, there's an x squared there and and of course an x. So the square root of that x squared is x. So that first one is 6x, the square root of 6x. Is that it?
Mm.
Yeah. The 3,
Yeah.
the square root of 24x cubed is the same as 6x, the square root of 6x. Are you okay?
Mhm. Yes.
Yes. Because you have written that as 3, the square root of 4x squared times 6x. Square root of 4x squared is 2x multiplied by 3 is 6x. Now, the second one is 5. Okay, let me, no. 5 times, I'm saying we want some mental, doing a mental thing. All right. Anyway, 5 times
6 times
54
9.
is 6 times 9, right?
Mm.
Mm-hmm. So 54 is 6
9.
times 9. So take
Yeah.
out the square root of 9 is 3. So 5 times 3 is 15, right? The square root of
Mhm.
6x. What remains inside is 6x. My question,
Yeah.
can you add them?
Yeah. I think so.
Yes.
So, of course, you
Just a
cannot add 6
radicand.
plus 15. No, that will not be. You can just put them together as an expression. So you can write that as 6x plus 15, correct? Times the square root of 6x. Is that okay?
Mm.
Because
Mhm.
we cannot add 6x plus 15. They are different terms. But of course, they are of the
Mhm.
same square root of 6x. So that will be your final answer. 6x plus 15, group that, and multiply by the square root of 6x. Is that okay? You can just ask question if you... All right. So the last 2 exercises, and then we will wind up. Yeah. This one is just subtraction. Mental math for letter D.
Oh,
Mathematical letter D.
Yeah, without using your pen. Let me see.
it's
So
Okay.
6 3. 6 square root 3.
Everybody agrees? The square root of 12 is the same as the square root of 4 times 3, correct? All right. But then the square root of 4 is 2. So 4 times 2 is 8, right? So it becomes 8 the square
Yes.
root of 3. Minus 2, the square root of 3 is 6 the square root of 3. Is that okay?
Yes.
All right.
Yep.
Yes.
That's easy.
Oh, that's easy. That's correct. All right. So it's 6 the square root of 3. All right. Do letter E.
Come on,
one-
do mental maths ne. For E. E.
You do
For
mental
E,
math.
that's the one mental math on, and it's like, my mind is too slow.
Why are you doing for E? It's D.
I don't know.
9, 16, 16. 16 times 5 is 80. Yeah.
All right. Yes.
I got square root 5x.
Mm-hmm.
I get the same.
Answer.
Square root 5x.
How about the others? Do you have the same answer? Any
What
other
about
answer?
the- Okay.
And she's like, hurry up, guys. I'm ready for lunch.
You're ready for lunch? You give the answer first.
That's why I'm telling you. Come on, stay away.
Yeah. This is one thing with having math when it's almost lunch. You go hungry and you cannot think. But it's also, I always wish that my math class would be, just in the morning. Unfortunately, I am 3 hours behind your time. So they have to schedule it so that it will not be 4 o'clock in the morning, my time. Okay.
What did you get?
Is that the square root of 5x?
Yeah, that's all.
Let's see. All right. So let's do that step by step. Okay. 380x is the same as 16 times 5x. All right. Minus 4. Your 45x is the same as 9 times 5x. Correct?
Yes.
Yes. Square root of 16 is 4. 4 times 3 is 12. The square root of 5x minus square root of 9 is 3. 3 times 4 is 12. The square root of 5x. 12 the square root of 5x minus 12 the square root of 5x. Answer.
5x. Well,
12
square root of
square root of
5x.
5x minus 12 square root of 5x.
The square root of 5x.
What is 12 minus 12?
0.
0.
0. Times the square root of 5x. What is it when you multiply anything by 0?
0.
So what's your answer? Is it square root of 5x?
No, it's 0.
0.
Oh, yeah, it's 0. Oh, please. Okay, so I hope that is you have learned a moral lesson. It should not be the square root of 5x. It will be 0.
I mean, minus in the same thing.
All right. So square root of 5x is not the same as 0. So your answer should really be 0.
So your mind is like 9 minus
It's like
9.
it's 1. There's
It will be square root of 5x if it were 12 minus the square root 12 minus square root of 5x minus 11 square root of 5x. Then that will be square root of 5x. But it's 12 minus 12 that's equal to 0.
So
All right.
minus 20.
All right. So yeah, we are just moving a little. Yeah, but I hope you will be so. We'll now talk about other things still on radical expressions, and then I'll move on with polynomials. If you can just read ahead, in your textbook, so that yeah, we can just. We are still in the introductory part of algebra, so maybe after polynomials, we'll be doing simplifying polynomials, we do a little factoring, then I hope that by next week Thursday, we can really begin with the real algebra, which is about functions. All right. So I will just put in the dashboard you need to do some exercises on this. Yeah, and whenever you do exercise, think of it as you're playing with numbers and letters so that you'll enjoy the work, okay? So, yeah, and yeah, you'll have a long weekend. Right? Yeah, so I hope you will enjoy your long weekend. And then can you be on this on one what do I say? I want to get a screenshot of all of you. All right, there. May I see? I want to see the faces. How will I have all of the faces very clear?
Everyone look at the Allen move.
How?
Move your move your
Yeah,
laptop.
but I'm only seeing three people. Where's Nate? Are there five of you in the class?
Yeah.
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 Yeah, I'm only of course I'm only I want to see each one on the having your own cubicle. How will it be? How will that happen?
Do that
I
because
see
it's
Manes. I see looks like I'm not seeing Rachel
Yeah, we
and Snake.
Oh, we could
How
all
do I
go to
see
that
all of
one.
you? Yeah, so before your long weekend, let me take a screenshot of our of our class.
Oh, go to,
I'll log in within mine, I think.
change the,
Oh yeah.
can't
Hey,
you,
log in with your own phones.
What?
Why not?
you mean we all go to Zoom?
No, just
Yeah.
me. And then we have two on mine and the rest through Owl.
Yeah, two on me.
Yes, log in on your phone so that you show your face.
Abigail,
Huh?
and then we put the owl there.
we
Can't you?
we still have 4
Then
minutes that you can spare before you go for lunch. Yes, Ne, I'm seeing you
go to,
now. Oh. Where is Rachel?
I'm here. There. All right, everybody come over here.
Oh,
We're going to come.
there. I want all of you to be just one. Go there and show your
And
face.
we're gonna face the screen. It's
Mm.
gonna be hilarious. Everybody,
Okay.
get over on this
Hey,
side.
I'm seeing you. All right. So yeah. So Rachel's name, Bethany, Abigail, Manish. Okay, now pause. Oh, very good. Okay. One, two, smile. All right. So I got you.
Go.
All right. Have a good you still have tomorrow and of course your long weekend. So I hope you'll enjoy your day and enjoy your lunch.
Thank you.
Okay,
thank you.
so yeah. All right. Okay. So let me
Yeah,
stop.
just
How
put
do I
it.
stop? Let me stop the recording.